are beginning to move into Chapter 4, and we're going to start Lesson 4.1 today. Chapter 4 is all about integration. And integration is going to be the second big topic that we study in Calculus 1. Our first big topic was the derivative, and it was all about the derivative, how we are able to use that to find instantaneous rate of change like velocity at a certain precise time. So integration is kind of working things backwards. Another cool thing about integration is it will approximate the area underneath the curve and above the x-axis for us. So if I wanted to find out precisely how much area this contained, all I have to know is if I can identify this function, I could give you the precise area. In geometry, remember how we kind of did estimation of areas? Well, we'll do a little bit of that too in Chapter 4, where we break things down into rectangles and perhaps into trapezoids and try to follow this curve, you know, ever so closely. And as you can see, the more rectangles I create here, the closer it follows the curve and the less overage or overestimation I have going on. So that's kind of where we're headed. This section 4.1 will work with antiderivatives, writing general solutions to differential equations. Use the indefinite integral notation. We'll learn what that's all about. And then, of course, we're going to pick up some integration rules to help us out on this. But let's just take a look at what you know so far. We've come a long ways in our calculus studies. We are able to take a function like x squared and give the derivative of it. Well, we all know that that is 2x. And that, you know, spots us on what is the instantaneous rate of change at some precise location at some value x. And I could, you know, give you the value of when x is 3, what is its rate of change? And I'd just plug it in here and I'd say, oh, I know that the derivative of 3 is 6. And that means the rate of change is 6 happening right at that precise point. Now what I want you to do is I'm going to give you the derivative and say, can you find what that original function must have been? Where did it come from? Where did this derivative originate? That's what we call an antiderivative, going backwards, finding the original function given the derivative. So if you could think in your head, what gives you cosine when you take the derivative of it? Well, you may answer to yourself, that was the sine function. The sine of x, if I take the derivative, I get cosine. So the antiderivative of cosine is sine. Looking at example 1 here, I picked up 4 different functions and they're listed across the top. What I'd like you to do is find the derivative of each of those. So the derivative of function 1 here would be just 4x cubed, wouldn't it? 4x cubed, the derivative of 6 happens to be 0. The derivative of x to the 4th minus negative 112 will be 4x cubed, and the derivative of 112 goes to 0. Here we've got our 4th function, x to the 4th plus some constant c, which means I just have some value for c. The derivative of that's going to be 4x cubed plus 0. Now, is that not strange? I have 4 different functions, but their derivative all is the same. Each derivative came out to be 4x cubed. And that's what we're going to talk about. This function is like a general solution for this antiderivative is a general solution for many precise equations. So that's going to come into play here. Antiderivatives and indefinite integrals are synonyms. They mean the same thing. I can say, please find the antiderivative, or please find the indefinite integral. So, let's see. Where do we got? We need to look at notation. This is our antiderivative symbol. Find the antiderivative. It's also referred to as an indefinite integral. This dx located at the end is written with the integral symbol, this tells us about the variable that we're going to use for integration. Now it could be dx, it could be dy, it could be dt, it could be many things. Whatever variable we want to integrate with respect to, it'll be notated here. We get our function, of course, right there, f of x. When we do the antiderivative, we are looking to come out with some function. Here you notice they capitalized it. It was like the original function. If I took the derivative of this, it would swing me back to this little f of x. And then, because this original function could have had some variable or some constant c, we're just going to tag on, when we make our antiderivative, plus c. This will be like a general solution to our problem. Inside here, this is called our integrand. It's the function that we're working with. Another way of looking at this as well would say, I'm taking the antiderivative of some derivative, and it'll bring me back out to the original function. Plus some constant. You'll get used to adding plus c when we're working with general integrals, or general solutions for integrals. Down below, I'm going to pass on that because we're going to try and save some time. Okay, so the shortcut rules, wouldn't that be nice to know? Some ABCs of integration. And I don't believe I put this on your note sheet, but let's just talk about a few of them. If I'm integrating a constant, I'm going to say that the integral then will be c, the constant value. If this were 5, it would be 5x plus some basic constant c. A second ABC of integration would be the power rule. This one is a big deal. We will use the power rule quite extensively. And what the power rule tells us is how to undo the derivative. So if I ended up with some function x raised to the n, the antiderivative is going to be add a power. So I'm going to take x and go n plus 1. And then it's also divided by this new power, n plus 1. Think about when I took a derivative. If I took the derivative of x to the fourth, the 4 swings down, and I have x raised to the 4 minus 1. So if I had x to the n, then I would bring n down, and I had x to the n minus 1. That was the power rule for derivatives. What we want to do now is we're going to start here from the derivative side and swing it back here. So I need to undo my function. So instead of subtracting 1, I'm going to have my n adding 1. So for this one, which turned out to be 4x cubed, I want to take this and work my way back here. I'm going to end up going x, or 4x, 3 plus 1. Swing it back up by a power. That'll get me back to this power of 4 that was original. And then I need to divide by this power as well. That is where this n plus 1 divisor is coming from. Because notice what will happen. I'll get the 4 to cancel with the 4. And this leaves me x to the 4th, which is what I originally started with. So if you can kind of follow my logic there, I know it's kind of scribbly, that's what we're headed to do. So that was the power rule. And there's several others. What if I have a constant times some function? So I've got a multiplier I can swing outside. You can bring that forward. Kind of like getting it out of the way, and we've done that a few times on other things. If I have adding and subtraction of two functions and I'm trying to integrate that, I can break it up into two separate integrals and deal with small things each separately. So take something complex and maybe break it down into something more manageable. Sine, the antiderivative of sine gives me negative cosine, and the antiderivative of cosine gives me sine. So I'm just pulling out a few of those trig ones. Here's e to the x. Well, the derivative of e to the x was e to the x. So the antiderivative of e to the x is e to the x. That's kind of an easy one to memorize. And then there's 1 over x. The antiderivative of 1 over x is natural log x. What I gave you guys was this sheet, and it has on the left side what the derivatives were, and then over here what the integration is. So if I integrated 0 here, it takes me back to c. some constant. And so this sheet will be somewhat helpful too. All right, let's apply some basic rules. I'm going to use the power rule on this, and I'm going to use the fact that I've got a multiplier. So I'm going to bring this multiplier out front, and then I've got x dx. Well, the power rule says if I have a function raised to a power, which I've got a 1 power there, I should take x and then raise it to an n plus 1. So we're going to have our 3 out front. I'm going to take my x and raise it by a power, and then I'm going to divide by this new power that I just created, the 1 plus 1. That'll give me 3x squared divided by 2 plus some constant. You got to have a c there at the end. Check it out. If you did the derivative on this, let's try to work backwards now. I would take 6, this would be 6x divided by the 2. Derivative of c is 0. This simplifies to 3x. It gives us back what we had started with over there, the integral of 3x. So this does indeed check out. The integral of 8. Well, I could swing the 8 out front. It is just a multiplier. And then I could say, okay, the integral of dx. Well, the integral of dx would be x plus c. So 8x plus c. Coming from this rule right here where I had some value and, oops, it actually is coming from right here. I'm sorry, I missed that. So my 8 was there. This became 8x. Next one, we have 3 separate terms. With adding and subtracting, remember there's that rule that you can break them up into individual ones. So if you wanted to, you could write this individually. It might be a lot of extra work to write it, but for the basics of learning today, it might not be a bad idea. So I'll just quickly jot this down. I'm going to be thinking of this as the integral of each individual term. Well, the power rule says we're going to take the power, add 1 to it, divide by that new power. And then next one is a minus sign, minus 3. I can swing that multiplier out front. So I've got the 3 out front. Now let's just integrate x. The integral of x is it had a value of 1, add a power, divide by the new power. Plus, moving on to the third integration here, I have 4, and then I would have, if I swung that out front, this really looks like 4x to the 0 dx, x to the 0, add a power, divide by the new power. Final step, don't forget to add some constant. So I get x to the 3rd over 3 minus 3x squared over 2 plus 4x to the 1st plus c. That would be the antiderivative of this polynomial. Adding a power, dividing by the new power. Sometimes it's helpful to rewrite before you integrate. So let's just rewrite this and get this power identified as the negative exponent that it could be represented by. Now integrate. This is power rule again. We're going to add a degree. So I'm going to take x to the negative 3, add 1 to it, divide by this new power. Then I need to add my constant in there. Now let's simplify. So this really becomes x to the negative 2 divided by negative 2 plus c. And I think I'm going to choose to rewrite that. The negative I'm going to bring up top. This will be 1 over. Drop this x because of the negative exponent. Drop it to the bottom as a positive. And then I had this 2 multiplier right there. So I'll have 2x plus c. There is my final answer. If you took the derivative of that, you'll find out it becomes 1 over x cubed. Rewrite. This becomes the integral of x to the 1/2 power dx. Okay, power it up. Let's add a power, divide by this new power, plus c. Okay, now x to the 1/2 plus 1 would be to the 3/2, and then I'm dividing by 3/2 plus c. I can restate this as this is dividing by a fraction, that's like multiplying by its reciprocal. So I get 2/3 x to the 3/2 plus c. And we've got this last one, 2 sine x. Maybe I would like to bring my 2 out front because it is a multiplier. And then all I have to do is concentrate on sine x. What gives me sine x? The derivative of cosine gives me negative sine, so I'm getting close. The derivative of cosine x gives me negative sine. So if I add a negative sign, I should be hitting this positive sign that I'm seeing, and then I'll go plus c. If you look on your integration chart there, you'll notice that the antiderivative of sine is negative cosine. And there's my final answer. Negative 2 cosine x plus c. Perhaps you'd rather see this negative attached right there because that was the antiderivative of sine. But then we'd still simplify out to that. Okay, so there are some tricks to learn about integration that maybe we can make things simpler for ourselves. Trick number 1 is to rewrite things, just like we just worked on, making that power that was sitting down below into a negative exponent. That's one of our tricks, rewriting it. Trick number 2 is to multiply or distribute things, such as in this case of letter A, and then sometimes separating fractions out can be helpful, trick number 3. So we know we can square this out. This would look like 3x minus 1 times 3x minus 1 dx. The integral of that, let's FOIL this now. Foiling that would give me 9x squared minus 6x in the middle plus a 1 dx. Okay, now it just becomes polynomial work. Each individual term we can integrate separately, and I will get the integral. That's the integral symbol. I want to, oops, I'm actually integrating, so I don't need the integral symbol. 9x to the add a power, divide by the new power. Minus 6x, it was a power of 1, so we're going to pick up a new power and then divide by that 2. We had the 1, x to the 0 is what's really showing there, add a power to it, divide by the new power, plus c. Simplify 3x cubed plus 3x squared plus x plus c. If you did a quick derivative on this, I'd get 9x squared. The derivative of this would be the 6x. Oops, I lost my subtraction sign, which comes right from there. And the derivative of x gives me the 1 x to the 0. It all checks out. Letter B, it said, up here it said, try separating your fractions. By that we can rewrite this one. We can go x squared over x to the 5th plus 4x over x to the 5th plus 5 over x to the 5th dx. Okay, then I would probably simplify again. That gives us an x to the negative 3, 4x to the negative 4, 5x to the negative 5 dx. Power rule. Power rule all the way. Power rule says if I'm integrating, add a power, divide by that new power. So I'm going to go negative 3 plus 1 divided by, that would be a negative 2, wouldn't it? Add, I've got the 4, put it down, just rewrite it. X to the negative 4, add a power, divide by this new power, which would be negative 3. Plus 5. X to the negative 5 plus 1 divided by negative 4. Don't forget to add the constant of integration, the c. Simplify, and we are done. So this will be x to the negative 2 divided by negative 2. I'm going to swing my negative up top. This negative I'm going to swing up top. I'd have 4/3 x to the negative 3 minus 5/4 x to the negative 4 plus some constant. Final step, negative 1 over 2x squared. Now I'm just writing my exponents with positive exponents, so I'm moving them down below so that I can achieve the positive exponent in the denominator. Final answer. That was a lot of work. Let's work on those in class because this is getting long.